Plastics play an important part in all aspects of human existence. Lightweight, disposable plastics are frequently utilized in our daily lives. By 2050, it is estimated that 26 billion tons of plastic garbage would be created, with half of it being discarded in the environment. Imagine a plastic bottle floating in the ocean. Years pass. The bottle didn't disappear. Instead, it breaks into thousands of tiny pieces. These particles become so small that they are almost invisible. They are called microplastics, with a diameter smaller than 5 millimeters. It has now become a global environmental challenge. Today, microplastics can be found almost everywhere. In rivers, in soil, and even insides are made of highly stable polymers. Nature struggles to break them down. Why are plastics so difficult to destroy? Most of them are composed of common polymers such as polyethylene and stable polymer structures. They can persist in the environment for decades. Think of a polymer as a long chain made of thousands of connected building blocks. They are held together by strong chemical bonds. Like a steel rope, the longer it survives. Scientists have been searching for ways to cut these molecular ropes. Several methods include biodegradation, thermal degradation, chemical oxidation, photodegradation. Each method has its own advantages and limitations. For example, biodegradation is environmentally friendly but slow. Thermal degradation is effective but requires significant energy input. Among these methods, photocatalytic degradation has attracted considerable attention because it can utilize light energy and potentially achieve complete degradation under mild conditions. Photocatalytic degradation uses semiconductor materials such as titanium dioxide. When exposed to light, electrons become excited from the valence band to the conduction band. Electron-hole pairs are generated. They react with oxygen and water molecules in the environment, produce highly reactive species such as hydroxyl radicals and superside radicals. These reactive radicals possess strong oxidation power. They attack microplastic surface and introduce oxygen-containing functional groups. This step increases the chemical reactivity. Then, the polymer backbone begins to break. Carbon-carbon and carbon-hydrogen bonds are cleaved. Slowly, the giant molecular rope begins to fall apart, reducing the molecular weight. The material loses mechanical strength. Scientists process chain scission. As degradation continues, they are eventually converted into simple molecules such as carbon dioxide and water. This final stage is called mineralization. However, although photocatalytic degradation shows great potential for reducing plastic pollution and improving environmental sustainability, several challenges still remain. First, many photocatalysts can only absorb ultraviolet light. Since most sunlight consists of visible light with lower energy, the overall utilization of solar energy remains limited. Second, environmental microplastics have different compositions, shapes, sizes, and chemical additives. These variations influence how they interact with photocatalysts. Third, complete mineralization often requires a long reaction time. Microplastics must undergo multiple degradation steps. To address these limitations, researchers are developing visible light-responsive photocatalysts that can utilize a much larger portion of sunlight. This approach can improve solar energy efficiency. Second, by optimizing catalyst structures and reaction conditions, it can accelerate microplastic breakdown and reduce reaction time. Third, researchers are exploring methods to lower energy requirements while maintaining effective photocatalytic performance. Finally, scientists are working to scale up this technology for real-world environmental applications. Large-scale systems are in oceans, rivers, and wastewater facilities. In summary, by generating radicals under light, photocatalysts can break down plastics into smaller and less harmful substances. Photocatalytic degradation represents an important step toward cleaner ecosystems. It could become a valuable tool in the global fight against plastic pollution.